this is Mrs. Yenny, and I'm going to talk about what to expect in Investigation 3. And in this investigation, we're really focusing on learning goals 1, determine the probability of a dependent event, and learning goal 4, finding and reasoning with expected value. And expected value is really what we're going to focus on the most. So let's just review what we know about expected value. Expected value is what we mean when we say like long-term average, or it's basically the payoff over the long run. And so to talk about expected value, I'm going to do a few examples. I'm going to do a 1-in-1 free throw situation example, I'm going to do a carnival game example, and I'm going to do a roll of a die example. And I'm hoping that those 3 examples will help you understand that concept a little better. Okay, so the 1-in-1 free throw situation, remember a 1-in-1 works this way. During a basketball game, you could either have a 2-shot free throw situation or a 1-in-1. And a 1-in-1 means that you get the first shot no matter what. If you miss the first shot, you're done. If you make the first shot, you actually get a second. And so it's kind of like a bonus. So here's Nishi, and she has a 60% free throw situation, which means over the long run, out of every 100 tries at the free throw line, she makes 60% of her shots. So we're going to use that information and figure out what's most likely to happen when she is at the free throw line. And so if you initially kind of predict what you might think would happen, she can either score 0 points, miss the first shot, not get a second shot at all, score 1 point, make the first shot, not make the second shot, or she, of course, could score 2 points, make both the first shot and her second shot. So most kids often predict that Nishi will score 1 point, that's the most likely outcome to occur. But what you're going to see here in a minute is that's not actually the most likely outcome. So what we're doing is we're going to create an area model, and you can see that I separated my area model into a 10 by 10 grid so that I'm really looking at 100 attempts at the free throw line, and I want you to think of it that way. So if she has a 60% chance, 60% free throw average, what that means on her first shot is that she's going to make 6 out of 10. So what I did is I separated my area model 60, 40. And so I put a little smiley face there. That's the chance she'll make it, and then a 40% chance that she'll miss. But remember, if she misses, and this is a 1-in-1 free throw situation, if she misses, she's out. She doesn't get a second shot. So that's why I put a 0 here. If she did make it, so if she's in this category, remember she gets a second shot. So what I did is I sort of turned the area model this direction, and again I separated 60-40. 60% chance she'll make it, 40% chance she'll miss it. So if she missed it, she's only earned 1 point overall. If she makes it, of course, that's where we get our 2 points. So now we can look at this probability area model and determine the theoretical probability of each of these point situations occurring. So the probability of Nishi scoring 0 points, as you can see, is 40%. Because, again, it's a 1-in-1 free throw situation. If she misses the first one, she doesn't get a second chance. The probability of her scoring 1 point is right here. You can see it was initially a 60% by 40%, so that's a 24% chance. And here the probability of scoring 2 points, as you can see, is 36%. 6 and 6. All right, so the reason that I'm talking about this is because this is a classic example of how to figure expected value. What is her expected value, or how many points would you expect her to earn on every trip to the free throw line? So to figure out that long-term average, we're going to take her probability percentages and apply them to the point values. So she's going to make 0 points 40% of the time, or 40 times out of 100. Think of it that way. So 40 times out of 100 times 0 points is, of course, 0. 24 times out of 100, think about what that means in terms of a percent. 24 times out of 100, she scores 1 point. And 24 times 1 is 24. And 36 times out of 100, she scores 2 points. And 36 times 2 is 72. So if we add up our 0, 24, and 72, we're left with 96 points, which means out of 100 times at the free throw line, we can expect her to come away having scored a total of 96 points. So we can average that over 100, but just by simply dividing that by 100. So then we would say that over the long run, we would expect her to score about 0.96 or 96 hundredths of a point every attempt that she makes to the line. Now obviously the scoreboard is not going to adjust to fractional point values like we have here. This is again an expected value. It's a long-term average over the long run. That's what we would expect over multiple trials. Okay, Okay, so that's the one-on-one example. Now I want to talk about a carnival game example. So in this carnival game example, we have this red-headed girl, and she designs this carnival game that is spin a red, flip a head for her red head. So we're going to spin a red on the spinner and flip a head on the coin. And if you do that, you get a prize of $25. But anybody else, anything else that comes up, you get a prize of $1. So that's kind of a great game. No losers, I guess. So the first thing we have to do in figuring out the expected value, so figuring out, in other words, what's expected over the long run. If I play this game multiple times, 100 times, what can I expect to win every time on average that I play this game? So the first thing we have to do is come up with all the outcomes that are possible. So what I'm going to do is I'm going to spin the spinner and flip the coin. And so I can see that I have 8 outcomes possible. 4 on the spinner, 2 on the coin. 4 times 2 is 8. And then I've listed all the outcomes here in an organized list. Red heads, red tails, orange heads, orange tails, and so on. So the probability of spinning a red and flipping a head is 1 out of 8. It's only one of those outcomes out of the 8 possible outcomes, which of course is 12.5%. The probability of everything else is, of course, then 7/8, or 87.5%. So to apply our expected value, I'm going to take that percent times my $25, and I get $312.50. And I'm going to take that 87.5, and I'm going to multiply that by 1, and I get $87.50. And so total, in 100 tries, because remember this is out of 100, in 100 tries I would expect to make $400 playing this game. So if I played this game 100 times, I would expect to win a total of $400. So to figure out the long range per attempt outcome, I'm going to divide that by 100 and I get $4. So remember, this is our expected value. It's the average that we expect over the long run. All right, the last example is a dice example, and this is just to simplify it a little bit. If you roll a die, let's say you get 2 points for a sum of 6. If you get 1 point for your sum, for a sum of 3, and you get 0 points for all else when you roll a die 2 times. And so to get a sum of 6, there are actually 5 out of 36 of the 36 outcomes that you can get a sum of 6. There are just 2 ways that you can get a sum of 3 out of 36. And so I have the probabilities worked out right here. And everything else gets 0 points. So this time I'm not talking about dollars and cents. I'm talking about point values. So 5 out of 36 is 14%. Remember, this is out of 100. Times 2 is 28. And then 6, of course, times 1 is 6. And then everything else is 29 out of 36, which is about 80, which gives us, times 0 is, of course, 0. So when I add this up together, I get 34. And, of course, this is already with 100 attempts. So now I have to divide it by 100 to get my long-term average. So I divide that by 100. And I would expect to earn, on every roll in this game, of earning 0.34, a little over 1/3 of a point per roll. And that's, of course, my expected value, or my long-term average. All right, I hope this helps you, and I hope that it helps you also to calculate your expected value on your carnival game for our math carnival that we'll be having soon. Thanks for watching, and let me know if you have any questions.